Next up, we have Xinwei from the Chinese Academy of Sciences, who will speak to us about new optical techniques to detect macro marine life. So Xinwei, are you there?
Yeah, thanks for Kitty's introduction.
Of course.
The moment I start screen.
So, yeah, there we go.
Can you hear me?
Yep.
Okay. Sorry. Oh. Oh my God. Oh, sorry. Okay, that's okay. Thanks for the invitation. This is my topic. I want to introduce underwater light ranging and imaging for macro marine life in-situ observation and measurement. I'm from Beijing. This is the outline of my talk. And firstly, I will introduce the background and motivation. As we all know, underwater optical imaging is important for marine life in-situ observation because it can grasp marine life pictures directly for researchers. So different kinds underwater optical imaging systems has been developed, and we can develop two types. The first is the microscopic imaging with micrometer scaled spatial resolution for macro marine life. And the second is the underwater camera with millimeter scaled spatial resolution for macro marine life. Here's the spatial resolution refers to the physical dimension that represents a pixel of an image. So from the pinhole camera model, and we can calculate the spatial resolution if we know the range between the target and the systems. Here shows an example of a microscopic imaging system underwater video profiler, and it can quantify the vertical distribution of zooplankton with more than 100 micrometers in size. Let's see how does the UVP work. That's a clever method. And we can see two LED are used, and then it can generate an illuminated volume of water. And in fact, the UVP is a dark field camera. It can only grasp objects images in sampling volume, and also the background field is dark. We can calculate the spatial resolution from this equation, and we get the spatial resolution. We also can calculate the object size from the target pixels and the spatial resolution. The UVP is used for biomass analysis successfully. For underwater camera, different from UVP, and the traditional underwater camera use laser or LED as lights, because at the deep sea there's a low light level, or even for dark, so needs active imaging with lights. And the image sensor is typically CCD or CMOS. For traditional underwater camera, the target with back scattering from water and also background can all be grasped. So the target to background contrast is low. The low target to background contrast is bad for target classification and identification, especially for turbid water. This shows the result from a paper scientific reports. It shows that the low contrast targets can affect the automatically extracted by the image classifier. So the question is, how can we develop a UVP type for macro marine life? So we want to develop a new underwater optical imaging system. It can observe macro marine life with the size centimeter scaled, decimeter scaled, or meter scaled, and it can also grasp high contrast images without background or with weak background, and also can obtain target range from between the target and the imaging system, so one can calculate the target size. Therefore, we propose a light ranging and imaging method, and we call it LiRAI. Let's see what's the LiRAI. And LiRAI can realize light ranging and imaging different from traditional underwater camera. It can obtain backscattering, target or interest, and background for LiRAI, and the target in sampling volume is grasped without back scattering from water, and also filter background. So one can also obtain two-dimensional intensity image and three-dimensional image. There are different underwater optical imaging methods. For example, the light and the camera is closed, and also to suppress the back scattering, the camera and the light is separated, and also develop ridge-gated imaging. And we based on the ridge-gated imaging to develop LiRAI. Let's say why choose ridge-gated imaging? Different from traditional underwater camera, and the ridge-gated imaging can suppress water backscattering and filter background. It can extend the detection range by a factor about 3, and so in this picture, as the volume of interest can be grasped. It works like the computed tomography. So based on the ridge-gated imaging, and James Bask developed a time slicing method for three-dimensional imaging. And from this picture, so if want to reconstruct a three-dimensional scene, that large data volume needed, and this will reduce the real-time performance. It is not suitable for moving targets, for example, fishes. So sorry. So we realize, so we develop a ridge intensity correlation imaging method for realizing LiRAI. In this method, a pulsed laser is used to light objects, and also a gated camera is used for collect the echo signal from target. The time control unit to synchronize the time delay between the gate pulse and the laser pulse. Therefore, we get two images, image A and image B, and based on the two gate images, we can obtain three-dimensional information from this question, and we also can obtain the sampling volume of the depths. It is related with the laser pulse wise. In the method, triangular range intensity profile is established when the gate pulse wise equals to the laser pulse wise. And based the range intensity correlation algorithm, we can reconstruct the range information from this question or from this question. So in the underwater imaging for LiRAI, the solid laser is used, but the pulse wise is fixed. So we want to realize different volume of interest grasp. So we developed a multi-pulse time delay integration method. This method can realize the depth of volume of interest adjustment. We can say that the LiRAI is different from UVP, and for the UVP method, we establish a illuminated volume of water by 2 LED. It is limited by the physical mechanical dimension, and for the LiRAI, and we use gated method to establish a volume of interest, and we can also construct target range, and the sampling volume can also be calculated from this formula. So the LiRAI can free from a physical mechanical size limitation, and also can reconstruct range information in sampling volume. Based on the LiRAI method, we establish a prototype Fengyan. This is the parameters of Fengyan. The laser average power is about 1.5 watt, and the laser pulse wise is about 1 nanosecond, and the minimum range resolution is about 5 millimeter. The spatial resolution is about 1 millimeter. The depth of the sampling volume is the minimum is about 35 centimeters. The depth range typical is from 3 meter to 8 meter. The maximum is about 20 meters. We can also choose ICSD or ICMOS for the image sensor. The maximum operation depth of the Fengyan is about 3,000 meters. So we can see the Fengyan based on LiRAI, the sampling volume can be a flexible adjustment. We can see this shows the result about 3 targets. This is 6 targets here shows, and also the 6 targets can all be grasped by the sampling volume adjustment Here shows the result of the resolution. The spatial resolution is about 1 millimeter, and the range resolution is about 4 millimeter. We also perform the sea tests in the South China Sea. Here shows the jellyfish at about 1,000 depths. We can see this is the two-dimensional intensity image. This is the depth map of jellyfish. We also obtained the sea floor at about 1,000 meters depth. Here shows how the Fengyan work, and we release from a mothership, and then the sea lander and landing on the sea floor, the Fengyan automatically worked when it finished the image acquisition, and then it flew up and recovered by a mothership. Let's give a summary. We try to develop a method for macro marine life observation and measurement. The method different from a traditional underwater camera. It can only obtain the images from the sampling volume. One can obtain the two-dimensional intensity image without backscattering or weak backscattering, and they can also filter background, and also can obtain the range distance of targets. In fact, the LiRAI is a kind of LiDAR, and as we all know, LiDAR is light detection and ranging, but different from LiDAR. LiRAI realize light ranging and imaging, so one can obtain a depth map and a texture image for target size measurement and target classification. In our opinion, that LiRAI maybe can give a solution for loss detection. As shown here, that the for fishes, they are also generate low contrast target problem. One can realize fish detection and measurement based on the texture intensity image and the depth map. We also find that Utopia also do the similar work and do some good jobs. If one interested can see this paper, and the Utopia realize automatic length estimation of free swimming fish, and so the two pictures here. For LiRAI, there's also many questions to need resolved. We also develop some method to dehiscing the images. Also, we can find that the pictures is the gray intensity image. How to realize colorful images is also a challenge for LiRAI. Okay, thanks. That's all.
Great. Thank you so much, Xingwei. That was really interesting. I think a lot of us definitely have challenges when it comes to sampling the mesopelagic zone. So yeah, I'm sure there's questions. First, Abby, do you have a question? Let's see. Abby, are you there?
Can you hear me now?
Yeah.
Oh, excellent. Sorry, I think my Bluetooth, something went wrong. That was a really great talk. Thank you so much. I found that super interesting. My question is, have you observed any behavioral changes in response to the the laser pulse. So, you know, for example, fish or zooplankton can be attracted to light. I was wondering if you've noticed any attraction from the laser.
No, we just perform a prototype, and we have do some experiment in the pool to watch fishes, but I think this is our future work to do.
Okay, thank you.
Thanks.
Great, thanks, Abby. That was actually a question I had too, was yeah, any kind of thoughts on a correction for avoidance behavior, but it sounds like that's something that you're going to look into in the future.
Sorry.
Yeah, that's all right. Are there any more questions from anyone? I have another question. How big is the LiRAI? Is it? Can you give us an idea of how big it is?
It's about the diameter is about 30 centimeter, and the length is about 40 centimeter. It's big because the computer and also the power is in the system. So how to reduce the size of the LiRAI is a big challenge, and we will do this work in the future too.
Of course. Any other questions? No? Looks like you covered everything. All right. Well, thank you so much, Xingwei. That was really interesting, and yeah, quite interested to see your future work. I would love to use this type of technology as well. All right. Well, thank you all for coming to this JETZON monthly Zoom call. We should have one next month, so I guess in July. So please let us know if you have anything that you want to share. We'd love to accommodate all talks, and yeah, so